Okay, welcome to the class. So it's glad to see everyone here. So it has been almost 1 year that I haven't been able to have a physical class. It was pretty exciting. But we're still dealing with the project issue. We are gonna have our first assignment today as a paper review. So at the later part of this lecture, I'll talk about how to review the PCI paper, where you can find good PCI papers, and then you will have to find your paper and do the review and submit a report of the paper of your paper review. And today the plan was to talk about basic neuroscience, about BCI, but since we will have a lab that's about implementing BCI system very soon, so I'd like to talk about neural monitoring and EEG efforts here first, and then I will put the basic neuroscience as video for you to watch offline. And meanwhile, we have started the grouping process. So basically, you have to find the members of the group by yourself, and each group will have 6 students at most, but we will assign the 6th member to you because there are a couple of lab members here, and we like to separate them into different groups so that will be better for the fairness since we have the competition at the end. And the 6th member, that is our lab member, will have to take care of the equipment. Because in May we will provide the EEG device to you to each group, and that's kind of pricey. So we have to make sure that the equipment is being properly managed. Okay, so they have this job. 好，那就是 这周本来是要上那个基本的神经科学，那不过为了就是之后我们有这个 DCI 实作的 lab，所以我们现在先从这个 neural monitoring 跟 EEG 的讯号截取开始讲。那确保说就是到时候实作的时候，我们就已经有一些讯号量测的这个技术跟知识。然后这个 basic neuroscience 我就把它放成录影，然后大家再那个再自己可以看看。哦，对，一点。OK， 刚才讲了，就是所以我们这周会有一个第一个作业，那是个人作业，就是那个 paper review 的部分。所以今天在后半的时候，我会用一些时间讲怎么样去找一个好的 DCI 的 paper， 然后去做这个 review， 然后到时候就是大家要交一个 paper report 的一个表。好，那 OK， so then we start the lecture today. Meanwhile, we have the online meeting and video recording going on. Because we have classmates as the quarantine still, so they will have to join us with the online meeting. Okay, so last time we introduced the system. Okay, we need to focus on. I'm allowed to take off the mask. So last time we introduced the basics of DCI system, and we know that the one first important step is to monitor the brain activity, so that we can know what the brain is going on. So let's go neural monitoring. So there are a couple of neural monitoring techniques so far. And here it's a summary figure that summarizes the different modality in terms of its size, its temporal resolution, so that you can see. So the vertical axis is about the spatial resolution, and the horizontal axis is about the temporal resolution. So here you can see different modalities at different positions based on its properties and limitation. So for example, EEG and MEG, that's on the top left. You can see that it has poor spatial resolution. So here it's millimeter. So the scale is about 100 millimeter. It's about 10 centimeters. So that's kind of one big part of your cell. And for temporal resolution, it works pretty good. You can see that it's about 1 second to 1 millisecond. So you can see that you can sense the rapid response in the brain activity. And on the other hand, we know some of the famous modality like fMRI. That's monitoring the blood oxygen level that's related to the activation of brain region. And you can see that it has better spatial resolution. So compared to EEG, that's about 10 centimeters. It's about 1 centimeter to 1 millimeter. So it can distinguish the difference between brain regions in terms of their activation for a specific response. And however, it has poor temporal resolution. So it can sense the change about 10 seconds to 10,000 seconds. So it does not sense the instant response in the brain activity. It rather sense the change of state of brain under different conditions. So to understand brain, we need to use different modality, and each modality can give us a good view for some of the brain activities, but there is no modality that can cover the whole picture, which means there's no modality that can give us the best resolution, best temporal resolution, or best spatial resolution. So we know that the best resolution, spatial or temporal, is on the bottom left. So you can see some like patch, clamp, and single unit recording. So they can provide very much information because it has very good resolution. However, these two modalities can only apply to a very specific region of the brain. So it does not cover the whole brain. So the observation scale is limited to like single neuron or the interaction between neurons, but it does not cover to like the brain region or the whole brain. So that's a limitation of different modality. 好，所以就是不同的这个量测技术，它们就是有不同的限制。那 EEG 它可能有很好的时间解析度，但是空间解析度就很差。那 MRI 的话，它有好一点的空间解析度，但是时间解析度就很差。然后虽然说像这种就是一个神经元或是这个 patch clamp 这种直接量测神经细胞放电现象的这种技术，它有很好的空间解析度跟时间解析度，但是这种技术它只能用在很微小的一块区域上，所以它只能观测到很微观的去看某一个或者某一些神经元的形态，它没有办法去同时观测到整个大脑。所以就是不同的技术会给我们不同对大脑活动的观测。那我们就是依照我们的情况去选择适合的modality去量测。So this is the basic structure of a neuron. It's a neural cell. So here you have the cell body, and it's extended with the dendrites and axons, where the dendrite can collect the messages coming from other neurons surrounding, and axon is for transmitting message to other neurons. So here let's look at different types of neurophysiological signals, because the activity of neuron is based on electrophysiological activity. So a lot of modality is monitoring the electrophysiological signals. So here, these are different types of signal we can record using electrodes. If you put the electrodes into the brain and it touches the neurons, then you can measure the activation of each neural cell. That's called action potential. So it rises the electro potential from negative 70 to about more than 100 microvolt, and create a waveform like this. And if you have an electrolyte in the brain, but it does not record a specific neural action potential, then it's probably measuring the local field potential. That's like the sum of electrical potential change in a local region. So that will create a waveform like this. So here you can see they have different requirements of sampling rate, because the waveform fluctuates in different pace. So local field potential, it requires about 200 hertz of sampling. Not sampling rate. So the signal has a response in this frequency region. So the sampling rate has to be higher than this to be able to capture a waveform like this. And this is the amplitude of this type of signal. And then you can see the ECOG signal. So that's the electrode placed above the dura mater. That's a membrane that protects the brain. So you're putting the electrode near the brain, but not in the brain. But it's underneath the scalp, so it's still an invasive modality. And that can record some signal like this. And EEG is a non-invasive approach. You place the electrode outside the scalp to measure signal like this. And you can see that it has signal that's less than 100 hertz, which means the information carried by high frequency signal has been lost during the conduction. So it retains the low frequency signal, and it has a amplitude around 5 to 300 microvolt. So that's the difference of the electrophysiological signal we can measure. And they are kind of related, but for example, EEG is related to ECOG. They might carry similar information in low frequency band. However, EEG loses the high frequency information. And local field potential is also related to ECOG, and local field potential is also related to the action potential activities. So from the inside of the brain to outside of the brain, you kind of expand the brain region that you're monitoring, but you lose a lot of information because now you're distant to the source of information. Okay. So these are the waveforms of local field potential and ECOG. You see they are kind of related. So this is from simultaneous recording. And this is the multi-unit recording of the action potentials. So here, the black dots shows the occurrence of action potential of a single neuron. So each row here represents the recording of one neuron. So here you have multiple neurons recording simultaneously. So you can see this, and this. They have some sort of relationship. Okay. So let's quickly take a look at action potential. So action potential is created by the polarization across the membrane. So we know that cell has a membrane to separate the inside and outside. So the ion concentration between outside and inside of the membrane is different. So that creates the electrical potential, because now you have different distribution of charge, ion charge across the membrane. So, but there are some gates on the membrane that allows the ions to go through. So when the gates open, you can see the ion flow inside or outside of the cell, and that changes the potential rapidly. So the active potential is created by the flow, the inside or outside flow of the ions, and that creates the rapid change of electrical potential across the membrane. And so that creates kind of a signal like this. You have this waveform that's from negative 60 or 65 microvolt to, I can read this, it's about, how much is it? This is about 40 microvolt. So this, the rising of electrical potential is called depolarization, because at the resting state, it's already polarized at around negative 65 microvolt. This is the process of depolarization, and then when it drops, it's called repolarization. You have the refractory period. 所以这个是那个 action potential， 就是神经元的一个放电的这个现象。那是因为细胞内外它的这个离子浓度不一样，那这些带电的离子浓度不一样的时候，它会在膜的两侧会形成一个电位差。那这个电位差会因为这个膜上有一些那个通道。所以当这些通道让这个离子流进去或流出来的时候，它就会造成这个电位剧烈的变化。然后，那神经元的这个放电的过程，它就会像是这样。那它这个电位上升的过程是这个去体化，因为本来这个正负离子不均匀的这个现象，我们把它叫极化。那你让它就是往上的话就是去体化，然后它接着会再下来，是因为它的这个离子进出的情况又改变了，所以它就再下来是再极化，然后再有一个恢复的一个时期。好，然后再准备下一次的方法。So the action potential is triggered by some excitation of the potentials. So these are, this is from, we know that, as we mentioned, the neuron has dendrites and axons. The dendrite collects a message from other neurons. So when other neurons is exciting this neuron, you will have a small potential rising from the dendrites, and it will accumulate. These will accumulate, and if the level has surpassed the threshold, then it will create a action potential. OK， 那就是那个神经元的这个 dendrite， 它会去收集其他神经元给它的这个讯息。那有一些是去激发的，有一些是去抑制的。那如果激发的这个 dendrite， 它就会产生一些这个小的电位上升。那这个小的电位上升，如果累积的足够多的话，它就会 trigger 出一个 action potential。So this is a cartoon showing how single unit recording works. You put the electrode near the neuron, and there's a ground somewhere else, and you can measure the difference between part and this part, and you can so that's how you measure the signal of action potential. And since the action potential is like a binary, has a binary behavior, it's either no or yes. So when we analyze the neural recording, we convert it into binary signal trains. So here, each row represents the firing of a neuron, and you can see the firing rate, which means how many firing occurs within a unit time. So here you can see the firing rate increase here, and if you add these, if you count these action potentials and sum them together, you can have a firing rate profile across time. So this is how many spikes per second you observed. So here you can have this, and in their experiment they found this is related to a specific stimulus. So here we can say that the firing rate increases after the stimulus occurs. So this shows a processing flow of neural codes. So here from the raw data, first you filter the data to detect the spikes in the signal. So here you can see the tiny spikes on the signal, and then you can detect each of them to extract a waveform within a fixed time window. And then you can find that the waveform are different, of course, between neurons. So the interesting thing is that a neuron will create the action potential in the same waveform again and again. And the different neuron will create different waveform. So you can perform some feature extraction or clustering to capture the difference of their waveform shapes. And then you can, in the clusters, you can separate them so that you can separate the different waveforms. Then you can distinguish the firing. I mean, you can identify the firing of each neuron, although they will be recorded together at the same temporal. OK， 那这边是一个分析神经放电资料的一个流程，就是 raw data 经过适当的滤波之后，你会得到这种讯号。那它把一些这个低频的震荡去掉，然后可以看到这些小小的 spike， 就是针状的这个东西。那这个针状的东西，你再去侦测它，然后把它用那个特定的 time window 把它截取下来，你就会得到这个 spike 的 waveform。那很多次的话就可以堆叠在一起，然后堆叠在一起，你会发现说这一条讯号的 spike 有不一样的形状的波形叠在一起。那因为同一个神经元，它每次放电的这个波形会一致，但是不同的神经元放电的形状会不一样，所以我们会发现波形不一样。那这个用讯号处理的方式的话，就可以去截取它的这个波形的特征，然后经过适当的这个群聚的分析，你就可以把不同形状的 action potential 标出来。那这样回到原来讯号，你就知道这个哪一个放电是对应到哪一个神经元。那像这情况下，就是有两个神经元放电同时被一个讯号连到。那用这样的方式可以把它分开。Then, so this is an example. You have a recording of but here you actually sense three neurons according to the difference in waveform。所以这边量到的就是它有代表3个神经元的放电，然后这边就是它们各自的放电，所以这个放电对应到的是这个，然后下一次另一个这个放电对应到的是这个，我们就可以去标出不同的神经元的活动。So this is an example of a visual experiment. So here you present the stimulus like this. So here the stimulus is the rectangular with different orientation. And this is the neural codes of one neuron that's related to the visual response. And for this neuron, they found that it has the highest firing rate for this stimulus. That's a rectangular in this orientation. And it has less firing rate for other orientation. So if you summarize the firing rate across different orientation, and you will find it has the highest firing rate when the orientation is vertical, and it has the lowest firing rate when the bar is horizontal. And the distribution is like this shape. And we call this tuning curve because here we see a neuron. The firing rate of the neuron is tuned by the orientation of the bar. And in another experiment, they record the activity of motor neurons, and they record multiple neurons. And the experiment was to allow the animal, like a monkey, to move its arm towards different directions. And then they record the firing rate pattern of different directions. So according to the tuning curve of each motor neuron, they are able to they are able to map between the moving direction to the firing rate of those motor neurons. So they can create a BCI that converts the neural firing of motor cortex to the cursor moving. 好，那这是另一个实验，它就是可能让猴子去操作，将它的手去往不同的方向去移动。那他们接着去量测这个动作相关的这些神经元，然后他们就会发现这些的放电特征，会跟不同的方向有关，然后他们就利用这个firing rate跟运动方向的关系去建立一个模型，然后就可以有这个 BCI 让这个动作皮质的讯号，然后去转换成它要操控的要动的东西，比如说是游标或者是一个机械手臂。So with this relationship, they are able to create a BCI for a monkey to control a robotic prosthesis for a cursor on the screen. Okay. So this is another type of neuron called spatial cells. Specifically, there are two famous spatial-related cells, place cell or grid cell. So the place cell, they found it when they put the rat in a region for free moving, and they found there are some specific neurons firing a lot when the rat is passing through this part of the space. And grid cell has a different types of behavior that it fires whenever it fires according to some grid pattern in the space, like a coordinate. So place cell kind of shows the different part of the space, while the grid cell kind of related to the coordinates or the measure of distance in the space. So the place cell was found by John O'Keefe, and the grid cell is found by Manfred Moser and Edward Moser. So they all won the Nobel Prize of Medicine in 2014 based on their findings on the spatial cells that kind of explain how the brain manages the navigation. So these are some real data recorded in the experiment. So this is the coordinate of the space for the animal to move freely, and these are the spatial place cell, and this is grid cell. And there are more cell related to navigation. So here you can find this vector cell that fires when the animal moves near the boundary. 好，那这些是这些真实的这个实验结果。那他们在这个动物身上就看到它们的 place cell， 它是在特定的区域方面比较强。然后还有 grid cell， 它就是会呈现这种就是网格状的这个 pattern， 那就跟坐标或是跟这个距离感比较有关。然后他们也发现有跟这个边界，当它靠近边界的时候才会发生这种事。Okay, so question so far? Good. Then next we'll talk about the basics of EEG. So as we mentioned, the EEG was from the electrophysiological activity inside the brain, and what we measure is mostly from the activity of the cortex. So in cortex there are a bunch of neurons called pyramidal cells. So they have this shape, and they are kind of aligned together vertically, and they have axon extended and aligned to each other. So when there's action potential created for the cell, we can find ion flow around the axon. And since they have the similar orientation, so the electric field, so they are likely to create a added electro potential change that can be sensed by the sensor outside the scalp. So again, this is the relationship between the single neuron recording to local field potential to EEG. So you can see that when the firing occurs repeatedly, you can see this kind of potential rising in local field potential. And that's related to this part of the waveform of EEG. 好，那这个 EEG 它是来自于皮质的一些 神经元的活动。那因为皮质这边有一种这个叫 pyramidal cell， 它们的排列非常的一致，所以当它们在活动的时候，它们这些离子流造成的电场变化比较容易被加成起来，然后被外面的这个电极所量测到。然后 EEG 这边也就是再重新再看一次，这个 EEG 跟这个 local potential 跟个别神经元活动的一些关系，那是有关联的。And this is ECOG electrodes that's placed on the dura under the scalp. And it's like a patch that comes with multiple electrodes, deployed like an array. So it covers a part of the brain with these electrodes. So if it's placed on like motor cortex, then it will record the something between EEG and local field potential. It's called ECOG signal around that brain region. So let's take a look at the YouTube video. So it probably has the instance of ECOG. So here they ask the subject to move the finger, and through the ECOG recording, the computer was able to decode the ECOG into the finger movement and showing by the robotic hand.所以这个就是他让受试者去动那个手，然后借由这个依靠，他就把它解读为这个手指的运动，然后让这个机械的手掌可以跟着运动。Okay, and we know that the flow of ions create a change in electrical potential, but we know that the electrical field and magnetic fields are coupled together, so it also creates a change in magnetic field. So while the electrical field is measured by the EEG sensor, the magnetic change can be measured by MEG sensor. And the first EEG recording was done around late 19th century by Richard Caton on animal. But the first human EEG was recorded in 1924 by a German psychiatrist named Hans Berger. So this is the signal he recorded at the time. So this is the EEG measure. And this is the reference sinusoidal signal around 10 Hz. So this is to show that from this one channel EEG, there are some waveform, oscillating waveform, like a spindle at 10 Hz. So he named this kind of waveform alpha wave. And the alpha wave is different across individual. Mostly it's around 10 Hz. And we also call it Berger's wave because this is found by Berger. And he also identified beta wave when the subject opens the eyes. And he also identified the epilepsy EEG. 所以这个是第一个 EEG 两侧。那这个是德国的精神学家 Hans Berger， 他在1924年对人类做的第一次测量。然后他就把这个波形记录下来，那这个是10赫兹的10赫兹的这个弦波，那对应的是这个它两侧道的一个通道的 EEG， 然后他就显示说这些波形呢，这个震荡的波形是在10赫兹，然后他就把这种波形叫做阿法位。然后另外还有发现了贝塔位跟这个癫痫的这个波形。So the alpha wave is the most phenomenal EEG we can see in our recording. So almost everyone has alpha wave when you relax. So the quickest way to induce alpha wave is to close your eyes and relax and think about nothing. And then you will find the alpha spindle in your recording, and we can use that as a control comments for our BCI. So that's why you will use in that one to use the alpha wave. That's the easiest way to allow your brainwave to control something. 所以我们第一次的 lab 就会利用这个 alpha wave， 然后让你去放松，然后产生这个 alpha wave， 然后去控制我们的脑机接应。And so here I'd like to ask, have you ever heard of Fourier transform? Anyone? So could you talk briefly what
I only heard.
I only heard of that. Okay, can anyone like use one sentence to tell us what Fourier transform is about? So Fourier transform, the basic idea is that any temporal signal can be decomposed into the summation of signal across different frequency. So EEG signal is a time series signal. So it can be decomposed into different frequency signal. So we can separate one EEG signal into different oscillations from low frequency to high frequency. And here, so conventionally we separate EEG signal into these frequency bands, delta, theta, alpha, beta, and there are also gamma. There are also gamma that's for higher frequency, but it's not shown here. So we can see delta has the slowest oscillation, and theta, alpha, beta they have faster oscillation. And while we can separate one EEG signal into different frequency, we can also monitor the change of power of each frequency. So here we can use the time frequency analysis to show the power change in one signal. Here you have y-axis for frequency and x-axis shows the time. So here we can see for example, the delta band has a power increase here around 500 milliseconds, while 10 Hz, that is alpha band, has a power decrease around 500 milliseconds. And for higher frequency band, we can see the beta here, it is around 15 Hz. The low beta band power increase around 1 second, that's 1000 milliseconds. So we often found that the power change of EEG is related to some change of brain state, change of condition, or related to some stimulation. And we can use that to decode our brain activity and turning them into some information. So here I'll quickly talk about what the frequency band is related. For example, the delta wave is related to slow wave speed. That's when you enter a deep speed into the deep stage of your sleep. 所以这个 delta band 它是最低频的一个频带，那它的波形就是慢的震荡，那它是跟慢波的睡眠相关。它就是因为我们把这个深度很深的这个睡眠阶段叫做慢波睡眠，那是因为它的特征就是会出现这种 delta 的波形。And theta wave is related to drowsiness or arousal. So usually when the drowsy level increase, we'll find an increase of theta band power. And it's also related to meditation. You can meditate, you can probably create this kind of oscillation in your brain. Theta band 就是跟想睡觉，然后还有跟这个静坐有关，它会产生这样子的 theta 的波形。So alpha, like we mentioned, is related to relaxation and eye close. And beta band is related to motor action. If you're doing some movement, you will see, this is mu band. So mu band has the same frequency band region with alpha band, but the mu is specifically to describe the 8 to 13 Hz around the motor cortex. And it's highly related to the motor action. So for example, if you execute a movement, you will see the decrease of power of your mu rhythm. And when you finish this movement, you will see the increase of mu power. 所以当你执行动作的时候，在这个动作频区这边，虽然它也是8到13赫兹，但是它特别被叫做 mu rhythm。然后当你执行动作的时候，这个 mu rhythm power 会降低。那当你结束这个动作的时候 mu rhythm power 会升高。So when you continue doing movement, you will see a stronger beta wave in your brain. And like we mentioned, there are higher frequency band called gamma, that's above 30 Hz, and it's relevant to neuropopulation activity. However, in practice, we rarely use gamma band as the information for BCI because the brain signal conducted to outside the brain, the decay find that it's more unstable and it's more easy to contaminate by noise or artifact. So we just use gamma as the information for PCM. OK， 那这个 gamma band 就是指30赫兹以上的地区。那但是在脑机界面的应用上比较少，是因为高频的讯号在经过传导之后，它的讯号非常弱。所以相对之下，这么弱的讯号，我们看到的这个平台可能就会有很多的杂讯或是 artifact， 那就会造成说我们不确定我们量到的是不是真正的这个 gamma band， 所以我们就比较去避免用这个来当做 ECI 控制的成分。Any questions so far? Do we have a break in between? Because I didn't hear the bell. So it should be from 11 o'clock to 11:10. Well, how about we take a 5 minutes break and we continue at 11:15.
我来给你打个。就是呢，我发现说，用中医来当我来跟这个是你们的话就，然后我们的话，对，我们是所以中国的是变成这样，所以中国的天气就这样，看哪个学校看起来比较顺眼，跟你们说，可以这样吗？不知道。
Welcome back. So here I'll talk about how to review a BCI paper. So for this assignment, I'd like you to review a BCI paper that's original research. Original research is one type of paper that's about they have an original idea and they have studied a question, a scientific question, using the scientific method to study this question. So here, original research will include, there will be a paper that describes detailedly about this original research, and it's the most paper you will find in a journal. And in this paper, it will include their hypothesis. They will introduce the background of this topic, and they'll describe their methods and show the results. And they'll also interpret their findings based on their results. And they'll discuss their results. They might have some implication for inference from the result, or they can relate their findings to other studies and to make connection to the field. And at the end, they'll probably have a conclusion to summarize the findings of this research. So the paper will contain about 3,000 to 12,000 words. And that's probably about 6 pages to over 10 pages. 所以 original research 就是你们大部分在查那个论文的时候，在卷里面可以看到的。那它就会包含它的假设，它就会先假设说，我如果怎么样，应该会怎么样。就是可能有一个科学问题，那他就要去先假设说这个问题的答案可能是，那我们要怎么样去研究这个问题？然后，那他的问题怎么来的？他会去介绍他的 background， 他是怎么样基于现在的一些看到的东西去发想出这个问题，然后他就会去介绍他的方法，他用来研究这个问题的方法。然后去呈现它的结果，然后去解读它的发现，然后去讨论它的结果，然后去说他们可能有没有一些推论，然后另外就是会去跟他们把他们的发现跟其他人的发现，过去的发现做一些连接。那这样子到最后就是他会推进我们在这个领域这个问题上的认识。然后它的长度大概是3000到10000字，那就是大约是6页，通常就6页以上，然后到10几页都有可能。And there are another type of paper called review article. So for this paper review assignment, I don't want you to choose a review article, but this is very helpful if you want to understand a research field, because a research article will provide critical and constructive analysis of existing published literature field. So they will summarize a lot of papers in this field from past to recent, and they might use the database to put some keywords and to summarize what they found through the search. It's called meta-analysis. So they will collect a lot of paper and then try to categorize or organize them into some maybe subtopic or some issues to discuss for you to quickly understand what the field is about and what the research is going on. And it will identify specific gaps or problems and provide recommendations of future research, with summary analysis and comparison. And generally do not present new data from the author's experimental work. So it's for review. So they will review a lot of papers, but they are not going to show some new result because it's original research paper doing that. OK， 所以就是 review paper 它就会去整理说现在这个领域大家在研究什么，然后遇到什么问题，然后未来这个研究大家会怎么做，来给一些建议。然后他就是在这个过程中，他就会去统整，然后去分析大家的研究，然后去比较大家的研究。然后它不会呈现新的 data， 但是因为 original research paper 通常才是负责就是呈现新的 data， 然后是一个新的原创的一个研究。And there are 3 types of reviews: literature review, systematic review, and meta-analysis. So literature review is to collect literature and describe what's going on. And systematic review may have some systematic organization to provide a better, more comprehensive or more comprehensive or more in-depth to convey their points in terms of reviewing papers in this field. And also meta-analysis, they might have some keyword research, and they might have some language processing tool to tell us from the paper database what we can find. Of course, so many papers. For example, they might have some language tool to extract some experimental results. So they might be able to summarize the data reported in different papers and to further perform some further quantitative analysis based on the literature. And so, okay, these are 3 types of review. And there are also many other types of articles. There are clinical case study, shows the clinical result of real patients' cases from medical clinical practice, and clinical trial. So clinical trial, it will describe the methodology, implementation, and results of the control studies usually undertaken with large patient groups. So this is usually part of the process of getting clinical certificate. So they will provide a large scale trial to verify a specific clinical approach. And there are perspectives that to review the concept or the prevalent ideas in the field. And there are also opinions that's for a specific, for an individual author's viewpoint of a field. And there are also commentary as a short article to comment or to criticize a paper or a book or a report. In many cases, people may see that there are some problems of the paper, and they can write the comments to criticize that paper, so that people don't get misled or an error or an incomplete conclusion or things like that. And there are also book review has to review a book. So here the aim of the book review is to provide insight on Indian recently published scholarly books. So for BCI, in the field of BCI, specifically for EEG BCI, the papers are mostly published in these journals. So here you have IEEE transactions from biomedical engineering. IEEE stands for an association of electrical and electronics engineers. So this association not only organizes events to common people, they also publish the research works in their transaction. So transaction is IEEE transaction is one type of journal, and they also have conference paper published by IEEE. So here the transactions on biomedical engineering is specifically for research in bioengineering. And there are also transactions on neurosystem and rehabilitation engineering. So this will be more focused on neuroengineering. And so you can feel that transactions on biomedical engineering will collect broader literature, while the transactions on neurosystem and rehabilitation engineering will be more focused on this field. We can kind of feel that this is the field of bioengineering. But sometimes there are some work that's more related to neuroscience that's probably kind of exceed the range of bioengineering. And there are also journal of neuroengineering. So in terms of the scope, these two are kind of overlap. But the Journal of Neuroengineering is published by another publisher. So IEEE is one publisher, and Journal of Neuroengineering, I think their publisher is named IOP. Yeah. And Frontiers in Human Neuroscience. So there's a publisher called Frontier Publishing Group. They have frontiers in many things, and one is human neuroscience. They also have frontiers in computational neuroscience, frontiers in neuroscience, and recently they have frontiers in neuroergonomics, and they also have frontiers in biotech and bioengineering. So many different journals. And there's also a journal called Brain-Computer Interface. So this is organized by BCI researcher recently. However, it's been kind of difficult to make this journal prominent because most of BCI paper goes to these journals. And they have already built their reputation and their impact. So BCI, so the Brain-Computer Interface journal is kind of difficult to get their impact factor, and which is very important to value the impact of the journal. So they're still trying to, I think they're still trying to grow their impact and to collect more paper. So to be as important as other journals. And some of the very important BCI research you will find in Nature or Science or PNAS. So these are some more impact journal that collects paper from a border field. So they collect almost all research of all field in natural science. So for a BCI paper to be published here, it has to be really important that has impact not only in the BCI field but also in the whole natural science field. So these are the journals you can find good BCI papers, and there are conferences as well. But for this assignment, I don't encourage you to choose conference papers, because this is not like the field of computer science where the most competitive publishing occurs in conference. Most good papers goes to journal in the BCI field. And conference paper, they have some nice new ideas being published, but a lot of them are not very completely studied. So I don't recommend you to review conference paper for this assignment. But this conference, I would definitely encourage you to publish your work and experience to BCI so that you can participate in this conference, because you can meet with other peers in this field. There are annual meeting of IEEE Engineering, Medicine, and Biology Society. So as I mentioned, IEEE is an association for all electrical or electronic engineers. And there are societies, so that's like the subgroup within IEEE, and one of the subgroup is called Engineering in Medicine and Biology. So most biomedical engineers can participate in their event, and this is the most important event as their annual meeting for this society called EMBC. And so the EMBC society not only hold their annual meeting, they also hold a meeting called Conference on Neuroengineering that's being held every 2 years. So it's more focused on neuroengineering. So a lot of BCI researchers will go there too. And there are IEEE International Conference on System Bank and Cybernetics. So the SMC is another society like EMB. So this is another subgroup in IEEE. So they focus like a lot of things, because it's like anything that's related to system and human and cybernetics. So so in the recent year, they emphasize on the BCI field. So they kind of welcome the BCI researchers to participate in their society and to join their conference. And then the International BCI meeting, so this is created by BCI researchers. And so they also created the journal Brain Computer Interface in the last slide. So this is held every 2 years, and it usually accommodates like 200 or 300 people. So it's a very focused meeting of BCI research. You will be very enjoyable. It's a very enjoyable event for a BCI researcher. So an original research paper will contain usually these sections. And the function of this section is to answer this question. So for after you've done the research, you want to show it to the world. You have to be able to describe it in a nutshell. That will be the abstract of the paper, and you will describe the problem as in the introduction. You have to point out the problem. You have to provide the background of the problem, the motivation you want to study this problem. That's all in the introduction. And you might have to review some other works that's dealing with this problem or very similar problem to talk about the relevant study and probably to distinguish the contribution of your work to theirs. And to describe how to solve the problem, that's in the materials and methods. And what did you find? That will be in the results. And what does it mean in this discussion? Who helped me out? That's in the argument. Like some individual that helped you with part of the research, although the person is not really involved. And you will also thank the grant, the funding you get for conducting this research. And whose work did I refer to? That's in the reference. That's all the literature cited. And extra information. So if you have too much to say, there are some limitation of the journal for the conference, and you have to condense your work into the depth of the article, and then all other things you think that's really important for readers, you put it to appendices for supplemental information that depends on what different publisher calls. 好，所以就是一篇 paper 里面呢，就是当你完成你的研究，你就要有办法，你想要发表出去，让全世界都知道。那怎么样很快的介绍你的研究，就是在 abstract 里面完成。然后你会介绍你的问题是什么？那这个问题就包含了你怎么样想要研究这个问题，你的动机是什么？然后有没有其他人在研究这个问题？那是 related work。然后怎么样引导出你要研究这个问题？那你这个问题是没有被研究过的，那它是怎样子跟其他人要研究问题不一样？所以要有办法去做这些区分，所以这都是在introduction里面要写出来。By the way, so you can see that in the introduction you will tell the reader what you want to do, but you will not show the results. So unlike abstract, you will describe your result and conclusion very quickly. There will be no information about your conclusion in the introduction. 就是你 introduction 里面你不会讲你这个结果是什么，那个是在 abstract 里面会简要的提到，然后在你的 paper 里面 introduction 你并不会讲，然后你会在 result 跟 discussion， 然后还有 conclusion 里面才会去讲说你的结果是什么。然后你的研究方法跟你用的这些东西，就是说就是在 material 的参与。那像 BCI research 可能就会讲你的 experiment。In BCI research, in the material and method, you might describe the experiment you design and how you conduct this experiment, and then how you collect the data and how you analyze the data. You might include some signal processing, feature extraction, or machine learning, and how you evaluate the performance of your BCI. So that would be your material methods. 所以 material method 在 BCI research 你可能会有做实验，就会介绍这个实验，或者你去用 data， 那你就会介绍这个 data。然后你可能会有讯号量测的方法、讯号处理的方法，还有
machine learning，比如说讯号辨识对 machine learning 的方法，然后还会介绍你怎么样去评估你的系统的效果，所以这些都是你的方法。然后你发现了什么，就是在这个 result 里面，然后discussion 就是讲说你的结果代表了什么，它是有它的含义的，然后还有你对它的一些推测、推论。那 acknowledgement 就是致谢，有谁帮助了你？然后谁帮助你就是可能有人，比如说有人帮助你，那个部分，虽然说他不是这个参与这个研究的话，他有帮助到一部分，那或者说你会感谢你的研究经费的来源，比如说科技是哪里，然后就会帮你致谢。然后所有的 paper 你用的就是在 reference， 通常是叫 reference。然后因为这个论文通常会有篇幅的限制，所以当你尽全力把你想说的局限在这个页数里面的时候还不行，但是还有一些是要觉得很重要的一些资讯，读者必须要知道的，就会放在附录，或者是有些地方是叫 supplemental information， 那就会另外附在外面，那它可能就不会算在页数限制。So this is about how to write a good abstract. So you can take a look here, and also for introduction and for material methods, result, discussion. So sorry, this is the information of the last year. So our paper reading report will due next week. So that would be 1 week from now, which is March 11th. And that's personal assignment, and you have to review a technical or scientific original research article related to this. And it has to be journal paper for this year. So today I will upload a review table. That's a format of your review table to the E3 so that you can fill out the review table. So that will be your paper review report. And if I have time, I will talk about how I review a paper. So this is an example. I choose a paper from the IEEE transaction on bioengineering. That's the title of this paper, and that's the authors. And in the table, I describe the scenario and the problem of this paper. So I quickly summarize what they have in the introduction and what they have in the results. And then I comment on their advantage of their study. So it includes their contribution, it includes the nice design of their methods, or some good consideration they talk about. And perhaps they have very good results, or very good presentation of results, or they might have some nice implication of the result in the discussion. And I also criticize the disadvantage. So they might have some, there might be something that they didn't consider, or there are some limitations in their methods, or things like that. So at the end, I give a final comments and suggestion to this work. 一个范例，就是我去 review 了这篇 paper， 它是1997年在国际财经期刊里面，它是开头的这个，然后我就这边会放一些基本的资讯，然后这边就是很快的去介绍它的这个研究的问题，那就是从它的 introduction， 通常就是从它的 introduction 你会找到这些 background， 然后它的研究问题会是什么。然后它的 finding 就会在它的结果里面，你就去看它发现什么。然后discussion 那边，就是这个 finding 有时候就是 result 那边秀出来之后 ，discussion 会再强调一次，然后 conclusion 会再讲一次，就是你从后半的 paper 就会整理出这些 finding， 然后你会去讲它的这个研究有什么做得好的地方。就是它的贡献有一些不错的贡献，或者说它的方法设计有不错的地方，它的这个结果的呈现的方式很好，让你可以理解的很有效这样。然后 disadvantage 就是它可能有一些没有考虑到的地方，那导致说它的可能结果有点局限，或者说它的方法设计上面就有一些限制，所以它可能只能做到这样，没有办法再做更多。然后最终就是对这个 paper 给他一个整体的一个评论，然后自己的建议，就是建设性的建议。Okay, so this is pretty much about the how to review a paper. Any questions so far? Good. So make sure you find a paper in these journals. Okay, so it's back to our lecture today. So there are some slides remaining. I hope we have time to go through them all. So event-related potential is a specific way to analyze EEG data. So we know that EEG data is a non-invasive modality, so it contains a lot of noise. It's unstable. So people found a way to increase the signal by repeatedly create the same brain response. So the way is to study the brain response to a specific stimulus. So here the example is a visual stimulus. So the subject will view a visual stimulus, usually from the screen, and then it's repeatedly presented, so the brain response will occur repeatedly. So here, S1 is the first stimulus, and S2 is the second stimulus, and S3 is the third. And you present the stimulus n times as all the same stimulus. And then you design a time window to extract the segment that's right after the stimulus. And then you can average them all by simply perform the arithmetic average. So the way we do this is that it's based on an assumption that any brain response that's triggered by this stimulus will time lock to the occurrence of the stimulus. And any other irrelevant brain response does not time lock to the stimulus. So after this average, we expect to enhance the signal and reduce the noise. So at the end, we can look at an average waveform we call it ERP, the event-related potential. So that will show the signal as time locked to the stimulus concept, which is 0 here. And these waveforms are extracted after the average of all the event-related EEG signal. 好，这个 event-related potential 是事件相关电位，就叫 ERP， 它是一种特定的分析脑波讯号的方法。它的这个用途是将这个脑波讯号的讯号增强，然后去减少杂讯，让你可以把特定的大脑反应抓出来。然后所以它的做法就是重复的去呈现这个刺激，让受测者一直看。那看到同样的刺激，那它大脑产生的反应会重复出现的，就把它叫做 ERP 的里面的东西。所以这个假设就是说，就是跟这个刺激相关的，它的反应就会在时间上锁定在这个刺激时间上。所以当你经过这个所有这些小片段平均之后呢，跟刺激时间锁定住的成分就会被增强。那跟刺激时间没有锁定住的，你就把它当做杂讯，然后它就会被我们的平均所降低，然后最后你可以得到跟刺激相关的所产生的大脑反应。And like I mentioned, fMRI and fNIRS record the blood oxygen level in the brain, in the brain vessels. So this is the basic idea of what being measured by fMRI pulse signal. So this is based on the neuroactivity when the neuron wants to when a part of the brain is being activated, the neuron needs energy to work. So it will send a signal to increase the blood oxygen level, and this can be sensed by MRI scanner. So we can see the activation of different brain regions, like here. So here there are, in their experimental design, they have evoked state and resting state. And for example, this is eye closed and eye open, and you can see the goal signal level changes according to the open or closed condition. And as I mentioned, fMRI has a good spatial resolution, so it can identify specific brain, like here, the specific brain region that's related to this goal signal change. And here you can see it's in occipital area, that's the part of both visual cortex. And fNIRS is functional near-infrared spectroscopy. It also records the oxygen level using the near-infrared sensor. And you can see the signal you recorded is fluctuate according to the stage, the condition change in the experimental design. And here you can see the temporal resolution is not as high as EEG or MEG. So you can see the fluctuation is about 10 to 20 seconds or more, because the change of oxygen level is not as prompt as the change of electrical or magnetic field. So here, this is the current non-invasive brain monitoring modality we have. Again, EEG and MEG measure the electrical or magnetic activity in the brain, and fNIRS and fMRI measures the oxygen level. So that creates a difference in the temporal resolution. MEG and EEG has high temporal resolution, while fMRI and fNIRS has low temporal resolution. For the portability, you can sense the portability by the equipment they use. MEG and MRI requires bulky coil, so their portability is low, while FNIRS and EEG, they can be portable device. But the cost, you can see that EEG has the lowest cost, so most non-invasive study was conducted using EEG modality because it has these pros and no cost. Again, this is a more detailed comparison across different modalities. So this summarizes the lecture today. Any questions? Then this is for today. Thank you for coming. I'll see you next week.
压缩的，所以好像没有。